So welcome, Marcus, thank you for the presentation. So I give you the floor, and I think you can start whenever you want.
Okay, let's start. So ExtraP is our insightful automatic performance modeling tool. And basically, it's a cooperation from the TU Darmstadt and from ETH Zurich. So you can see there's two colleagues on there from ETH Zurich. First of all, Alexandru Calutoiu, who originally had the idea for ExtraP and developed it a long way. And now me and Alexander and Benedikt Naumann basically developed further tools for ExtraP and advanced it in several ways, but I will show you later what we did. So if we take a look at the general spectrum of performance analysis methods, basically we have a range from, on the left side, benchmarks that can usually handle a large number of application configuration parameters, going to full simulations, model simulations, and models. Usually, models can handle the least amount of parameters, but also we have like a high model error. But on the other side, models are much cheaper and easier to come by than running full-blown benchmarks. I'm sure everyone here knows that already, but ExtraP basically now is on the model side here. So usually what's the motivation behind using ExtraP? The motivation is that we find basically latent or hidden scalability bugs in our parallel codes. So usually when we deal with a parallel code, we start out on a small system represented here on the left side. Basically this is our small cluster. And then we have this stuff animal here that now represents basically the computation and the communication part of our program. So we do testing on a small cluster, and then usually if it works fine, what happens, we want to scale our program. So we go to a large machine now, and then suddenly if we run our program, we still have the same amount of computation that we want to do, or maybe a bigger problem, but suddenly we have much more communication overhead, and we're not exactly sure where this comes from. That's exactly where ExtraP comes into play. So what we do with ExtraP is we create so-called scaling models. So a scaling model basically represents the performance metric as a function of the number of processes, and then provides insight into the program behavior at different scale. So we can see that here in this plot. Basically, we have on the left side our runtime of a specific function, or the total program, let's say, and on the x-axis we have the number of processes. So our scaling model basically shows the runtime as a function of the number of processes from the program. Yeah. So now there are a few different methods basically you can create such a scaling model. One of them is analytical performance modeling. So basically you would go ahead and analyze parts of the program and then identify kernels that dominate basically the performance at larger scales. You can do that either through intuition if you're the developer and already know your code, or maybe you run like a few small scale tests. However, that process is quite laborious, and of course you need an expert, because you need to know about the program and you need to know how to do this testing and find the bottlenecks. And on the other side, it's really time consuming, and it's easy if you have a large program code, it's easy to overlook basically a small part of the code and miss like a bottleneck. So our solution for that is automatic performance modeling. So better said, empiric automatic performance modeling, because what we do is we run small scale experiments, empirical measurements basically, that you can see here. So we have a program, just program main in this case. We have a few methods, foo, bar, compute, and that's our first input. Now we go ahead and do instrumentation of this program and all of its functions. And then based on that, we get performance measurements, empirical performance measurements. So we do this measurements not just for one configuration of this application, but we do it for several. This means application configuration means, for example, the parameters that I use to run the application. So if we have our batch script, we might run the same problem size for our scientific code, but we might use another number of processes. So we might use like 16 processes, 32, 64, 128. So we take different measurements of the application at different scales. And then in the next step, we can use these measurements with ExtraP, load them into ExtraP, and ExtraP will automatically create for us human readable performance models. These scaling functions that you saw before, one might look at this, like T for the runtime of the application, with a coefficient, a logarithmic part that represents the number of processes, P here. And then, of course, you also get a graphical representation, as you can see here, of the scaling model. The primary focus of ExtraP is on scaling trends, so identifying scaling trends. Usually, a visualization of a performance model that you see in a paper looks like that. So the data here looks quite clear and is somehow directly available for the reader to see what is the scaling trend in this performance data. So, however, usually if you take a look at the actual measurements under lab conditions, it looks more like this. So you can see here, maybe for the first few 2000 number of processes is still fine, but then it starts to spread apart and your measurements are not so clear anymore. In a real life production scenario, measurements on the cluster look more like this because, of course, you have other jobs going on. You have noise from OS, from networking, from different sources. And then your measurements look more like this. And as you can tell, now it will be much harder to predict accurate performance models. So that's why our primary focus is basically on identifying scaling trends. Now let's come to how we create our performance model. So for that, we basically use different building blocks. Yeah. And with these building blocks, we model on one side, of course, the computation part of the application, but on the other side, of course, also the communication part. So these building blocks are basically the lowest level entity that we use to construct our scaling models. Therefore, we have a few different of these. We have a classic constant building block, so it's just a constant value. Then we have a logarithm with a parameter, for example, could be the number of processes, the p here in this case. And then we have a polynomial. And then, of course, we can have a combination of all of these. So here we have this fictive function sample sort, and the scaling model here is basically the runtime as a function of p, that might be the number of processes. And here we have basically a combination of a polynomial part, a logarithmic part, and for the computation. And if we look here, another example for the communication part, this communication part from the sample sort could be just a polynomial, for example. Or for this FFT kernel here, it can be just a constant. So now that we have these, take a look at these basic building blocks, let's take a look at our performance model normal form. We use this formula to construct performance models. So as you can see here is, again, we have a function of a parameter, could be the number of processes. And then we have a sum where we can have basically a combination of these different building blocks together with a constant, and then have multiple of these. Yeah. And now what we also can do is with this performance mononomial function is we can restrict the search space. So first of all, with the n here, we can determine how many of these building block combinations we can have. So this combination here, we would call it a function term. So n here determines if we are allowed to have 1, 2, 3 function terms, or maybe even more. And then we have these two sets I and j here, basically, that determine the exponents of these building blocks. So the set of I here basically determines that for p here, for this polynomial small term here, we're allowed to have a 0, a 1, and a 2 as exponent. And the same goes for j and the logarithmic part, basically. By using this, we can restrict or enhance the search space as we want, and come up basically with different hypotheses that we can then test against our data. So a search space might look like this. So this could be just a constant function, a constant with a polynomial, a constant with a logarithm, a constant polynomial logarithm, and so on. And then, of course, with different exponents as well. So as you can see, we can also extend this here in the later part and add several function terms. And it gets complicated pretty quickly, and you see we can create a huge search space, basically. So let's take a look at our workflow next. So as I said, everything starts with the performance measurements here as an input. Then we usually have our performance profiles. Performance profiles we call basically just the recorded measurements that come either from a tool like ScoreP, I will go into that later, or maybe you recorded it by yourself, the time, just using MPI timers, for example. The first step then, what we can do with these performance profiles is we can do statistical quality control. Usually, as I said, we measure different application configurations, and we also advise to take several repetitions of each configuration, because then if we do a statistical quality control at this first step, we can already find out what is the variance, for example, in these measurements. Do we get roughly the same values, for example, runtime, for identical application configurations, or do we have already a huge variance that could mean that we have a lot of noise? And then maybe we could take even more performance measurements, or for example, we could identify outliers, take them out, and then use our performance data for modeling, which in the end will also result in better models. So then we usually go ahead with model generation. Model generation works like I just explained with our performance model normal form. We span up a search space, and then to do a form of linear regression, basically check against the data, use some statistical quality control, and create our models automatically. We refine this several times internally in ExtraP, and it will basically automatically give you the best model that we can find based on the data that you gave to ExtraP. In the next step, then the scaling models can be used for performance extrapolation. So it means now we can use the models and scale them, for example, the number of processes, and then check and make a ranking of the kernels. So meaning we can identify which kernel's performance will be dominant at a specific scale. And then with this information, the developer of the application could, for example, go into specific kernels and do some refinement. And then we would start the process over again, take measurements, check the performance again. And basically, we can do this over and over until we are satisfied with the performance. So there are some assumptions and limitations to our tool. First of all, generally we assume that there's only one scaling behavior for all the measurements. So this would mean that there are no jumps in the performance behavior. So a lot of MPI operations, for example, have a switch where they basically change the algorithm based, for example, on the number of processes or the resource that you allocate to your job. So here on the right side in this plot, basically you can see this. The black dots here are our performance measurements representing time in this example. And as you can see here clearly, from 2 to the power 9 processes, something's happening because the scaling behavior of our kernel is clearly changing. So before we have the square root of x, and after this 2 to the power 9 processes, we just have more linear relationship basically. So that's an example how an MPI collective operation switch can change a performance model. Generally, we assume that there are no such jumps in our performance behavior that we are trying to model. So usually what we do is we rank growth rate according to this big O notation, basically. So we have different types of scaling behaviors in this big O notation. As I assume you would know, we have constant, linear, polynomials, exponential, and of course like a lot of subsets in these. And now for ExtraP, sometimes it's hard to say which growth trend or which function has the dominating growth trend, because it really depends how you look at the data, and that's what I'm going to show you now. So here we have two functions. We have this logarithmic one with the p, and then we have the square root of p. And if we look at the visualization here, we can see that from a certain point on, basically the square root of p function will be dominating the runtime. Yeah. However, if we zoom in, respectively zoom out of the picture, we can see that here on the left side, the square root function with the logarithmic one is a dominating one. And then if we zoom out again, basically this function here, the logarithmic one, is the dominating one. So in both cases here, we have the same two functions, but depending on how you look at the data, you get a different result in our kernel ranking. So basically that tells us the user already needs to have some kind of expectation basically for what scale he roughly wants to have a prediction. Because without that, it's really hard to say what will be the dominating growth trend just according to the data that we look at. So as I just said, kernels are ranked according to lead order terms in the models. Therefore, we use this big O notation. For example, OX comes before OX power of 2. And now let's come to an important thing, of course, like how do we conduct this performance measurement? So basically, there are different ways of collecting performance measurements. One of them is ScoreP. I put the link here for you if you're interested in ScoreP and didn't heard about it so far. Basically, it's a profiling tool, and it will allow you to automatically instrument your entire application and create performance measurements of it. So you don't need to do any manual instrumentation, and you can also automatically ScoreP will record runtime, for example, and other things, but you can also tell it to record puppy counters, for example, if you want to count the number of floating point operations for specific kernels. So as already mentioned before, we require you to measure different configurations of your application. We need at least 5 different configurations because this is a requirement to our modeling method. Let's say we would just have 2 points. So if you would just have these 2 points over here, basically the only function, since ExtraP in the heart is still a function fitting approach, The only function we can fit here with 2 data points is basically a linear one. So we need at least 4, but better 5 points, so we can really identify if we have a linear trend, a polynomial with a logarithm, maybe an exponential trend. And if we have exponential functions, it would be even better to have more points. So we have these performance measurements of different configurations, as you can see here. P1 to 5, for example, a number of different processes here from 256 to 496. And then we can use these for modeling. As I also said before, we would like to have several repetitions of these different configurations, because if we take a look at the actual measurements in our chart here, we see there is some variance in the measurements. So there are some differences. For example, especially for this one here, where we have 2 to the power 10 processes, something happened and we have a huge spread here. So it might, if you have something like this here, it would be interesting, for example, to take more measurements and then identify what are the outliers, what is the variance on them, and see, okay, maybe your actual performance behavior is like that. And here you just had some noise influence on the cluster because there was like a communication bottleneck because other jobs were running. So as I just said here, the noise would be too big, the variance is too high, and you will get bad results for modeling. So of course, what we also do is statistical quality control. As we just take a look here, basically, if this is the case, the confidence intervals for our model will be too wide. And then basically the model fit will be not optimal on our data, which will lead to less accurate models in the end. On the other hand, what we do not want is overfitting, because if we fit our model too perfectly on the data, in the end, we will also lose prediction accuracy for at larger scales, what we actually want to do, because we not just want to fit a model on these training points that we have, basically. And to do this is what we need, exactly different repetitions of the actual measurements that we take of the different configurations. And the best thing, like I said, the first step of our modeling workflow, do a statistical quality analysis of these measurement points, find out the variance, see if there's a lot of noise, and then work with that and take more measurements. So we have our first statistical quality control measure here using this confidence interval. Another thing that we do to find out which models are good or not is basically we use the adjusted R2 metric. This R or R square metric. Basically, this metric represents how well the determined function fits our training data, our available measurements that we use for modeling. So generally, the higher this R square value, the better is our model. So if we would have an R square higher than 0.95, it would indicate that we have a model that fits our data really well, and in the end should be also very accurate. If we have R squared of 1, it could even indicate that we have some overfitting and that the prediction result actually might be a little less accurate. Now I will get into a few advanced topics, ExtraP, so a few modifications that we made over the year. So we created a new version, ExtraP 3.0, where we introduced fast multi-parameter performance modeling. The background for that is, of course, that not every application has just one configuration parameter. In the end, usually we want to analyze several parameters. I already mentioned the number of processes a lot, but you could also want to adjust your problem size, for example. We call it n here in this example. Or you would maybe have an order of a solver parameter that you want to change, or you could have a result precision parameter. So now with this addition, ExtraP is able to handle multi-parameter performance model and consider basically the performance difference. So here down you can see an example for a model with even 4 parameters. Yeah. So to do this, we expanded the performance model normal form. So the difference basically is that we introduced here this product. Yeah? And with this product, basically we can have different parameters per function term. So we still have the same basic building blocks, constants, polynomials, logarithms, but now we can have basically multiple parameters in one function term, and then we can combine them in different ways. So we can combine them in an additive way, or in a multiplicative way, or even a way more complex way, basically, where we just combine addition, multiplication, and mix the function terms with each other. Then in the next version, ExtraP 4.0, we introduced what we call sparse modeling. Because sometimes experiments can be very expensive, it was hard to get the full set of measurements that we required with ExtraP. So let's say you wanted to model your application with 2 parameters. In this case, the number of processes and then the problem size. You would have need basically 25 different configurations of your application. So you would have need to measure 25 of them. Now what this chart shows here, that sometimes if you want to run these different configurations, you can run into 2 problems. Either if your problem size is too big and you are running this on just like one node or with a few processes, you get memory issues. And on the other hand, basically, if you run a very small problem size, but with huge number of resources, basically the main effect that you could measure is the system jitter. So both is not good, and it's difficult to find the right configurations of your measurement of your application that you want to measure. Therefore, we introduced the sparse modeling that let you more freely choose the points that you want to measure. So instead, now with the sparse modeling, you only need 5 points, different measurement points per parameter. So for example, for the number of processes, it would be enough to have these 5 black points here. And then for the problem size, it would be enough to have these gray squares. So you would just need actually 9 points instead of 25. And of course, you can measure more points, what will lead to having a better accuracy, because in the end, more data is always better for a function fitting method like we have. Now the question was, how do we choose the configurations that we measure? For that, we did a lot of analysis and basically ended up with this heuristic guideline or strategy. So you should always start by measuring the minimum amount of points required for modeling. Then use ExtraP to create the performance models. And then we need to ask ourselves either how much money or do we want to spend for the performance measurement, or what is our budget? And if we still have budget, we can gather additional measurements and then create a model again with ExtraP. And then we can do evaluation basically. So we can evaluate our new model against the old ones and check if we saw some improvement. If we didn't see any improvement, we don't necessarily need to do additional measurements. If we saw an improvement, we could keep going if we still have budget until we find our final model basically. So of course we evaluated the sparse modeling approach for synthetic data, where we actually could reduce the average modeling cost by about 85% on synthetic data. And then we did the same for 3 case studies, fastest crypt key and relearn. And so it also showed that basically for all of them, we could decrease the modeling cost by like a huge factor, as you can see, 70%, 99%, 85% for relearn. And in return, we just get a slight increase in prediction error. Now, of course, it's to say we can still get the same prediction results. There doesn't need to be larger error, but of course we have to use more points, what will cost us more. So what we tried here is basically we wanted to see how far can we go, how far can we decrease the cost and still have error that is like kind of acceptable. So in some cases, it might be that you could decrease the cost by only 50%, but you will have only like 1% prediction error more. Yeah, so you have to find a sweet spot there. So let's get into how we can use ExtraP 4.0, which is the current version release that we have. There are a few requirements for you to install ExtraP. The first one would be Python 3.7 or higher. So the current ExtraP version is completely implemented in Python, and therefore the other dependencies are also a very commonly used Python package. One of them would be NumPy, and the second one is PyCubeXR. It is basically our own implementation of a cube file reader. And then there's a few other Python dependencies for the GUI and a few also that the GUI runs on macOS basically. ExtraP is really easy to install on all systems, so you can run it on Linux, on Windows and on macOS, as I just said. And therefore you can simply install it with pip. So if you have the package manager from Python installed, you can just basically do python -m pip install ExtraP and install ExtraP. If you already have a version installed, you can use this -upgrade option to force the installation of the new version. And the good thing is with this package manager, all of the dependencies will be installed automatically, so you don't need to worry about anything. So for this workshop, I already shared the version of ExtraP with you in the chat, but here's the link again. You can simply go to our GitHub page, and then you will find, first of all, a documentation of ExtraP and a little guide how to get started with it and how to use it, as well as some sample data. And then basically you will see there is two tools or two applications that you can run. So one is specifically targeted for command line version. So if you are working on the cluster and if you do not want to run or use a GUI. And the second one is a graphical user interface version that you can run on any system. And of course, also the command line version, you can run it on your local laptop and not just on a cluster. However, the GUI version is not intended to be used on the cluster, so don't be surprised if it doesn't work, even with some tweaks. Okay, so how do we do performance modeling with ExtraP? Little recap here. So first of all, of course, we need our performance measurements, and then we do the instrumentation of this application to get the performance measurements. For example, we use ScoreP for that. Then we get measurements. In the case of ScoreP, we get a cubex or cube profile file. You will get several of these. As I said before, we measure different configurations. So here with this profile file, you can see the parameter P and how it changes. So these are our different configurations. And then we have this R here that also indicates if we did several repetitions of the same configuration. Then ExtraP will take this profile, these cube profiles, and will, depending on if you run the command line version or the GUI version, either give you a textual representation of the data here, where you can see the model and the region that you modeled, or it shows you the graphical representation, basically. So now if we want to model a set of cube experiments that are coming from ScoreP, we need to know a few things. So our modeling file accepts these cube files from ScoreP. However, there needs to be a certain, let's say, naming convention for these files. So usually we have a directory for these cube files, and you will just select the directory with ExtraP, and then it will read all cube files in there. So each cube file then should have a prefix, for example, the application name. And then we basically have different parameters. So you would have, for example, P for the number of processes, and then we would have postfix that would be the number, the actual number. So we have P and then, for example, 8, and then a dot R, and then a number that indicates the repetition of this configuration. So if we get this naming convention right, it's pretty easy to load the data into ExtraP. We just open our input menu and select open set of cube files. And then the only thing we need to do is either select if we have weak scaling in our measurements or strong scaling, and click OK, and ExtraP will load the data for us. So let's take a look at the visualization options that we have with ExtraP. So first of all, this is the general user interface of ExtraP. So there's a lot going on now, but let's take a look first at the different panels that we have here, basically. On the left side here, we have what we call a call tree exploration, yeah? Where you can see all of your call paths or your kernels, basically, and the models that we created for them, where you can select the kernel to visualize them. Then we have a plot here. So this is the visualization panel of ExtraP, where you can see your models, compare them, show the data that you measured. And then on the right side here, we have another panel that let you adjust the performance modeling approach that we use. And for experts, basically set a few options to either improve the models or basically configure the search space also. So let's take a look at this call tree view first. The first thing we have here is basically this combo box where we can have different models. So for one application, if you load the data, we can create basically multiple models and then compare them with each other. I will show you that later in the hands-on session. And then we can also have multiple metrics. So if we work with ScoreP, as I said, it already measures for you runtime and other things, and maybe you have counters as well. So here you can select the metric that you currently want to look at. For in this case could be time, but it could be also visits or floating point operations. And then here, basically, we see our call tree. So all of the kernels that we instrumented and measured. And what we can see is not only their name, but we see the performance function that was created by ExtraP, and we see a few statistical quality control metrics here. So we, for example, have RSS, we have our adjusted R-square value, we have the relative error, and so on. Then a cool feature that we have in ExtraP is we can automatically look at the asymptotic behavior. So you see we have this slider down here. And this slider basically sets the currently used number of processes that we use with this created performance functions here. So if we adjust the slider to the left or right here, on the left side here, this color indicator will change. And basically this color indicator tells you the impact of this specific kernel here on performance. So what we can do is we can analyze which of these kernels have a dominant performance at a specific scale by manipulating this slider down here. Okay, so for the plotting panel, of course, we visualizing the function that you clicked on, And then it also shows you basically in the left corner the selected call paths that you're visualizing at the moment. Additionally, it can show you the measured values that you have. You can select if you want to see the average of them, the median, min, max, or show all of them. So you can visualize all of the data that you measured basically. And then you can also adjust this plot view, of course, here. You can select your parameter and then specify a maximum value to look at different scales and scaling trends here in the plot view. So another thing that we can do is we can simply create performance models from text files. So as you see here in our input dialog, we also have the option to open a text input file. And in some cases, it's either not necessary to use a tool such as ScoreP because the overhead is too high, or we just want to do some quick and dirty fast measurements, then it would be easier to use something as timer in your code and just print them out in the text file. So that's why we created this text input format. And it's basically pretty simple. So you have to follow this order in order for it to work, but it's pretty simple to do it like that. So first of all, we have a parameter and the parameter name. So basically the left side here are work like tags. So it lets our reader know what data is coming up in this line. So first of all, we have our parameter. And then we can specify one parameter or several separate by commas, or we do it in different lines and tell the application what is our parameter for the model, in this case P. Then of course we need to tell the text reader what are our application configurations. And we do this by using this point tag here. Basically tells the reader now are the different measurement points that we choose coming up. So this would be for the configurations 1000, 2000, 4000. So basically that are the values of P, the different configurations of P that we measured. Then we have a tag for the metric and the region. So we can specify the upcoming data that we give to the modeler is for this metric runtime and from the region main, for example. And then with the data tag, we can specify the data for the first point, which would be 1000. And then we can have several values here. We could have just one, if we just did one repetition of this configuration with 1000 for P, or we can have up to 5 or even more. And then in the next line, we would specify the data for the next measurement point, which would be 2000, and so on. Now, as I mentioned, we can of course also use the command line tool. For example, if you're working on a cluster, if you want to see the different commands and options that we have for that, just also visit our ExtraP GitHub page and you will find the documentation there. So basically it's as simple as typing ExtraP. And then the first important thing is you need to choose the input file that you want to load. So it could be either a cube file that is coming from ScoreP or a text-based file that I just showed, but we have more input options. So there is a JSON format, for example, as well. And after you specify the type of format that you want to read, you just need to provide the file path. So creating models can be as simple as that, as having ExtraP, the type of the file that you want to model, and the actual file path where the input file you want to read is located. The output ExtraP then will create for you basically looks like the following. So it's a textual-based representation of the visual one. First, we can see the call path that was measured, that we instrumented, This would be compute in this case, and then we see all of the metrics for this call path. In this case, we just have one for simplicity, the runtime. And then we can see the measurement points with the values that were measured for the different configurations of our application. So let's assume we have our number of processes and we ran it for 2, 3, 4, 5, and 6 processes. And then for each of them, we have from the different repetitions, we computed a median and a mean value, and we use these for modeling. And then, of course, we also get the model that ExtraP has created for us, and is automatically the best fit model that ExtraP found. And then in the end, you will have also some statistical quality control metrics that will tell you how well that, for example, here the R square that will tell is 1 in this case, and this will tell you that, okay, the model has a great fit on our measurement points, basically. So let me give you a small introduction for the hands-on exercise that we will do later. So we will try to play around with ExtraP, and therefore I would like you to go to this website here and download the example dataset. I also shared this link in the chat with you, so please go ahead and download the dataset, as well as go to our GitHub page and try to install ExtraP. We will then try to basically open the datasets in the GUI and the command line tool and play around and see what kind of models we can come up with and analyze them using the different graphical visualization options that we have, or produce some textual outputs as well. And then in the end, I would like also, after we do the hands-on, I would like to collect your feedback and see what maybe additional features would you like to see in ExtraP. And of course, if you find any bugs, you can always contact us. Either we have a support email list here. If you also have general questions regarding ExtraP, you can write us a question here, or you could also use our ticket issue system that we have on GitHub. So this would finish basically the presentation part. And now I would go into showing you a few examples using ExtraP.
Okay, thank you, Marcus. I don't know if there are any questions about the presentation so far.
Oh yeah, sure. If someone has a question about the presentation, please go ahead and ask.
I have one question, Marcus. Most of the examples I have seen are for modeling computing models. So do you have also models for mixing I/O and computing of pure I/O applications? Pure I/O models or not?
We can also model I/O. So basically, if we have the data, we can model almost everything, since it's basically a function fitting approach. But my colleague Ahmad is also currently working on specifically modeling I/O requirements.
Okay.
So if you're interested in that, you maybe can also contact him. He has a really interesting approach modeling I/O requirements, but we can also create I/O models with ExtraP, or communication models and so on.
Okay, thank you.
Okay.
There are more questions?
Yeah.
No? Okay, so I think you can continue, Marcus.
Okay, so I think before we do the hands-on, I will just basically show you a little bit around what we can do with ExtraP. So I've got it installed here as a Python package. So basically it's as simple as just typing ExtraP GUI in your terminal, and it will show the the graphical interface. Let's get that a little bigger. And you can see it looks like the one that I showed you on the slides before. So basically, the first thing that I would like to show you is we working with some text files. So I have an example text file here. This text format I talked about earlier for a very simple example. So you have just one parameter x, you have different measurement points, and then you provide a region, compute in this case, and a metric time. And then for each of these configurations here, we provide several data points. And now we can just open our file dialog here in ExtraP and say open text input. And then select our file here and open it. And then ExtraP, since it's just a small file, it's really fast. And we just need to select it here. And ExtraP automatically now created the performance model already for it using the data. So you can see here we have this model panel switch where we can select the model. There's just one now. And we just have one metric because there was just one in the data. But now what we can do is we can, with this modeler panel over here, we can create different models basically for all of our data. So I can provide a different name, second model maybe, because I decided to, maybe it's better to use the median of the data set, and then I click generate again, and then we have another model. So here now you can switch between the default one and the second one. And you can see if I do that now, actually the model changes a bit. Not much, since it's just a constant before. But it does matter if I use the mean or median values of these measurements here, basically. So what ExtraP will do is for all of the data here, for one of these configurations, it will compute the mean and the median for these, and then you can choose to either use one of them for modeling. So let's do the same, but this time with a cube file. So we have this folder here that I call Blast. Is from the Blast case study that I have. I think is code from Lawrence Livermore National Lab. That's doing some physics simulation. And now for this code here, you can see we measured a lot of different configurations. So our parameter here was the number of processes, starting from 64 until 16,000. And then for each of these configurations, we did 5 repetitions. So here you can see the naming convention that we use for each folder here. That is necessary, otherwise ExtraP can't read the data, because it needs to know somehow which data belongs to which measurement configuration. And if we go into one of these folders, we see there is some ScoreP configuration files, but the important one here is this profile.cubex, which is basically the measurement data file that was created by ScoreP. So let's go ahead and load this cube file as well. So I'm just need to select this main folder here, and then, like I said, I can select if we have weak or strong scaling here. In this case, it was a weak scaling experiment, and then just press OK, and ExtraP will basically load the data set. This takes just a second because now it's much more data than just in the text file. So you don't have to wait every time. There's a hack for that. I will show you also. So now you can see it finished loading the data. Now it's already modeling. And we got a warning message. So what we do when you load the input data is we do a little analysis and check actually if there is data for all of the measurement points and metrics. And if we find out that there's not enough data to model one metric, for example, we exclude it and then let you know. So in this case, we had metrics, task migration loss, and bytes get, bytes put. These ones are automatically recorded by the score P, but we didn't find enough data, therefore they're excluded from modeling. So now what we have is a much more interesting example, because as you can see, we have a huge call tree of different models for different kernels of the application here. So that's all that was instrumented basically in our score P files. And now we again just got our default model that was created by ExtraP on a startup. And you can see we have a lot of different metrics that we can choose from. At the moment, we are taking a look at the visits. You can see our main math parallel main function just says one visit, makes sense. And then, of course, we have also our model for the visits metrics. And then we can switch, for example, to time. Maybe the runtime is a little bit more interesting for this example. So then we can select basically the call path or the kernel that we want to look at, and then view it here in this visualization panel. So, like I said, we just not have our models here, but we also have this quality control metrics, RSS, our R-square value that tells you how well the model fits our data. So that's how you can also control how well this model is. And now what we want to do is maybe we can try to optimize these models, and we can do that by creating another model here with our model generator. So standard, it uses the mean, but let's use the median now. And then we have some advanced options here basically. So we can specify if for our function creation, for example, we wanted to allow to use log terms. If we want to use cross-validation and other stuff. And basically, if we already have an expectation of how our application will perform, we can also specify the exponents that we allow for the polynomial part, like this, for example, and maybe like this for the logarithmic. And if we generate the models, then basically we can restrict the search space to our expectation. Or we could, for example, also, if we tick this here, we can use negative exponents as well. So we had one use case where we had to have negative exponents for our models. Yeah, but let's do something simpler. Maybe just disallow the log terms here. And then if I press generate, you will see ExtraP will generate a new model. And now we don't have any functions with a log term anymore. If that makes sense now for the specific example is questionable, but that's how we can adjust the modeling method depending on our expectation and knowledge about the application and tune our models basically.
Sorry, Markus, just
yes?
one point. Could you show also the sample points?
Sure, yeah, I was going into that. So another thing that we can do is we can show basically the measurement data that we recorded. So if I right click here on this plot view, you can see we have a few options now. The measurement points are hidden. But for example, we can show the mean points. Let's make this a little bigger. And then you can see basically the measured points for our configurations that we had. Or we can also show the minimum, or we could show the maximum. And if we show all points, then you can basically see the confidence interval that we have and the function that ExtraP created in this confidence interval. So you basically see that this function here now is very close to the median values that were computed of these points. Yeah? And another cool option that we have, so if you're not sure about the performance that you will expect from the application or not, and you don't know specifically about the search space and how you want to set it, we have another modeling generator that we call refining. Because what it does is basically it automatically refines the search space by itself. So it will start with a standard search space and then refine it make it larger or smaller based on where the data it's leading basically. So you don't need to think about it. It will not always turn out with optimal results because it tends to over optimize on that. But it allows you to get better models if you don't have expectation already. So now you see we have with log terms again our models. And of course, we can also adjust here the view. So we measured until 16,000 something processes in this case, but we can also set this to 64,000, for example, and then we can see basically how well or how this function of this kernel will scale for the runtime and the number of processes. So we can make it even larger. See, then we can take a look at that. Another thing that we can do is basically we can select two functions at the same time and then look at them and see which one has like the dominating growth trends. And now, like I said before, what we can do is we can do this growth trend analysis, but for specific scales. So we can use this slider down here for our parameter and move it. So now you see all of these models basically use p equals 1. So now if we change this here, you see suddenly also on the left side here the colors change, yeah, from the different kernels, and the colors basically indicate the dominance of the kernel of the runtime at this specific scale that I have selected right now. So now let me show another thing, because what you can also do is you can save the experiment that you're currently working on. So we have the option here to save this experiment, and then you can basically just type a name and save it. Oh, okay. I think I already had that file. Let's start it up again. I already prepared one for this example, basically. So from another application that we have, this one with 2 parameters, because it's more interesting for the visualization. I will show you with that one. I had worked before. So as you can see now here, there's a lot more measurements because we need these for 2 parameters. And so we have the number of processes here and the problem size, basically. Now, if we would just load this from all of the files we have, it takes a long time. So that's why I created the experiment before with ExtraP and saved it here as this faster save ExtraP. And now what we can do is we can just click here on open experiment, and I will load this fastest experiment. And now it will load everything from the experiment file. So you can either just start off where you left last time, basically modeling, or you can just load it once and then save it, and then the next time you don't have to load it from the cube profiles anymore, which saves you a lot of waiting time actually. So now we have a 2-parameter example. You see this one is much larger. There's a lot of kernels that we modeled, and that's why it also takes so long to open it. Again, let's take a look at the runtime. And now what we're gonna do is I'm gonna show you the different visualization options that we have. Let's see. Okay. So, and now for the scaling model analysis, you also have 2 parameters you see. So you can modify the problem size. Here's the function I was looking for. This is one of the solver functions basically from this application. And now we can, if we adjust the problem size, you will see here the solver that's doing the actual work will also become the bottleneck and not some MPI init function. And at the same time, we can also adjust now the problem size as well, the number of processes, I mean. So we can now basically individually change or play with these around to see where the bottleneck will be depending on our resource and the allocation and the problem size that we select. And now we can also try to select 2 files at once. So you see the model is also more complicated now with 2 function terms. So we have our size model parameter and we have our number of processes now. And then we can take a look and compare these with each other basically. Again, we can also show all of the data points. In this case, you see this example had a lot of noise actually on it. It was measured on SuperMOOC. So you can tell there was a lot of noise on the system, and it's quite hard to interpret the measurements for ExtraP and create these models. So that's, like I said, one step that you always have to do is quality control with your measurements. That's if we just select the median points. You see as well, there's a lot of variance in our data, basically. So again, of course, now we have 2 parameters. We can also play around and change the second axis as well. And we can then zoom in and zoom out here to see what is the growth trends at which point. So you see if I increase the x-axis, we see the functions cut each other another time here, and from there basically the growth trend from the orange one will be bigger again, which is this sub P2. So if we go larger than 10,000 process, actually this one will have the dominating growth trend again. With the visualization now, it kind of depends. We have different visualization options for you. Of course, it depends what kind of data you have, if they make sense or not. So for this example, this line chart makes sense, but for a 3-parameter example, it doesn't work anymore because, of course, you can't see your data anymore. Here is also tricky because you can't directly see the size parameter. We can switch that here. So we can make the x-axis show the problem size instead of the number of processes. But for this scenario, basically, we have another visualization options, and these are the surface plots. So now you can see both your number of processes and the problem size, and you have this surface plot basically that shows you both of the functions. And then of course, again, you can kind of also manipulate the axis here. We have more visualization options. For example, we have one here that shows you basically a similar thing, but it also shows you the measurement points, yeah, as well. And you can also always save like this specific plot. So let's take a look at that. And then maybe you already have like a graphical representation for your paper, or you can just look at it later and don't need to start up ExtraP anymore, basically. We also have contour plots and other color plots, but I won't go too deep into this stuff now. I think you can also try out by yourself in the hands-on exercise later. However, what I would like to do is give you a short example with the ExtraP console version. So I made myself a little cheat sheet here, and what we want to do now is we want to model our text file basically with ExtraP in the console. So again, maybe I can make my font a little bit larger. Yeah, so you can see better. So again, we need to type ExtraP, of course, for our tool, and then specify with -- text. We can specify the file path and the type of the file that we want to load. And if we just press enter now, basically ExtraP will load the file, will generate the model, and then print the output to the console. So in this case, we just had this compute call path, the metric runtime, and then we get our measurement points here and the model that was created by ExtraP. And again, we have our R square is 1, so it indicates a good fit. If we just type ExtraP, basically, it will give us a usage example with the options that we have. So it is mandatory to specify the input type and the file path. So you can see all of the input types here. And then we can specify, for example, if we have a weak or strong scaling, also if we load a cube file. So let's say we want to do something similar like in the GUI. So for example, we can decide to use the median values of these measurement points here instead of the mean. So what we would do is we load the file again and just put -- median, and then it will create the model, but with the median. And now we should actually see again a change here in the constant. Yeah, so the constant here was -0.8, and here is actually -1.4. So it worked. Another thing what we can do is we have different modelers, like I said before, but if you're not sure which modeler features which options, you can also use our help feature that will basically tell you for the refining modeler in this case how you use it, and then which options you can specify for the modeler. Because in the end, the command line tool has almost all of the features besides the visualization, of course, than the GUI version has. So then let's use these options like in the visualization tool and specify, for example, we want to use the median, we want to use our refining modeler, and we do not want to allow log terms. And then we get the same model in this case because it didn't have a log term in the first place, but basically that's how you can adjust the options for the modeler and the modeler itself that you want to use. Another thing that might be important is we can not just print the output here in the console, but we can actually also print it to a text file. So if I do -out and then specify the file path, we still get our print out here, but now we should also have, yes, we have a file here that we wrote the same result set into basically. Then what we can also do is we can manipulate this output. So for example, maybe we're not interested in these measurement points. We just want to see the created functions. So in this case, we have this print option where you can specify what we want to print. So I just specify functions, and then ExtraP just prints you the functions of the models that it created. Now, of course, we can also use the cube format like the GUI before, but it will also take a while to load it, and then ExtraP will basically automatically show you all of the call paths and all metrics in this format here. And then if you use the cube as input options, the same goes as with the text file. You can either specify the modeler you want to use, the modeler options, if you want to write it to a file, or if you want to specify what is actually printed. So you could also just print the functions for all of the call paths and metrics, or you can, for example, print just the call paths if you want to have a list of the call paths. So now it loaded the data. It again tells you that some of the metrics were skipped because there was not enough data, and now we're generating the models basically. So, and now we have our output for all metrics. You can see you have bytes received, bytes sent, and so on. And all of them each for the call path that we have here. So this would be a parallel MPI receive, and then we have all of the metrics for it, the measurement points and the models. And then here would be our parallel MPI finalize. And then we have another one, parallel main MPI all reduce. And so we have all of the data here basically. And now you could print it to a text file again, or just print the measurement points, just print the call path, print all of the metrics, print just the functions. Yeah, so basically what you can do or can take a look at in the graphic tool as well. So that basically finishes the demo part, and we would go to the hands-on session now.
Thank you, Markus. Can you just show maybe a JSON file which can be used as an input, because we thought of using it?
Yeah, sure. I just need to pull up one. Give me a second. Okay, so if you go to our ExtraP GitHub page, so this is our ExtraP GitHub page here, and of course you find the source code, but you will also find the documentation here and the requirements, how to install it, etc. You will find the options here for the command line tool and how to use it. But if you're searching for some test data, like Amit just said, you can go to tests here and then to data, and you will find basically synthetic examples for all of these files that we use for our integration testing. Doesn't matter now, but let's take a look at the JSON formats that we have. So here we basically have our JSON format, it features the same information than the text file. So again, we specify our parameter and the measurements, but it's a little bit different since it's JSON and is basically stacked in each other. So we have per measurement, we have always specify first the call path and then the metric, and then inside an array, basically, we provide the different measurement points directly with the values. So we have our measurement point for processes, and then we have all of the values for each repetition, and that we have basically for every call path and metric. And if we look at the second one here as an example with 2 parameters, so now we have just an array here where we specify both parameters, and then here this also changes that we have an array with the values for the measurement configuration here, and still the values, and then here for sweep we just not have time, but we also have the number of visits instead, and then we have, let's see here, another call path sweep 2, and then time again and visits. So you see it's pretty straightforward and easy, this JSON format. So are there any further questions regarding ExtraP or the presentation?
Hello?
For now? Yeah?
I have a question.
Okay.
In the last command prompt, you showed how it works. I have a question that in one of the models, it showed none. Is it an expected behavior? For example, it's Hindi bytes sent.
Oh, so that's actually one thing I'm still working on right now. So here the case is the following. So as you can see, for all of the measurement points, actually the data that we get here is 0. So for all of the configurations, the data is 0. That basically means that in this case, no bytes were sent for this call path. So of course now we can create a model that is 0, but in this case I just made like a modification that prints like none here, because it doesn't really matter if you have a model that's 0 or if you don't have a model at all, because it doesn't tell us anything. I'm still working on like a convention that I can tell basically if it's better to have 0 or no model at all. That gets basically important later if you compare like different models with each other, or for example, if you are trying to summarize models from different call paths. For example, if you look at this tree, there's always like a tree, a main tree node, and then you have these sub call paths. And if you're trying to summarize them later, I just put this none, so ExtraP knows, okay, it skips like analyzing this path because there is no model there. But yeah, thank you for the observation. Maybe I should change that for the user.
Thank you. It's really helpful. I just wanted to know.
Yeah, I'm running like an experimental version actually on my computer. That's like, I think it's not actually what the behavior you're gonna get on the if you download the version.
Yeah, okay, thanks.
Thank you, Marcos. A pleasure. The presentation has been very useful. Thank you again, and I think that's all, no?